8.4 covers algebraically defined vectors and the dot product. So let's start with the definition of what a position vector is. A position vector is a vector with initial point at the origin in a rectangular coordinate system. If you have a position vector, we'll call it U. It's a boldface U, not italicized. With the endpoint at 8b, it's written as vector U equals with the angle brackets AB. So if we want to draw a position vector here, we can start it at the origin and go out whatever our magnitude is. And if that endpoint here is the endpoint AB, we say that this vector U is AB with angle brackets. And we have both horizontal and vertical components. The horizontal component is your A, and the vertical component is your B when we're talking about points, and it's the same way as a vector. This is your horizontal component and this is your vertical component. So geometrically, while in the previous section our vectors, we represented them as directed line segments, algebraically they'll be this ordered pair in angle brackets. The magnitude and direction angle of a vector, AB. So our magnitude is given by this formula. The same notation as before. The magnitude of vector U is equal to the square root of a squared plus b squared. And you can imagine why that would be the case if we're starting here and our vector goes as such. We have this being A, and we have this being our B, and so our magnitude is the length of this hypotenuse of that right triangle. So this is just the Pythagorean theorem working for us here. The direction angle satisfies tangent of theta equals b over a. So if this is your theta here, then tangent is opposite over adjacent. So nothing new, we're just applying our right triangle trig to vectors now. So let's try this out on these two problems. We're going to find the magnitude and direction for these vectors. So if we want to call this vector U, then the magnitude of vector U is the square root of the square of the horizontal component plus the square of the vertical component. And so then I have 49 plus 576 under my square root. That's going to give me the square root of 625, which is 25. So we have a magnitude of 25 for this vector. And the tangent of theta is equal to the vertical component over the horizontal component, and we'll use our inverse tangent to figure that. So inverse tangent of 24 over -7, making sure that you're in degree mode, and we get a theta of the calculator will put out a -73.7 degrees. So what we want to do though is make sure we add 180 degrees to that so that we end up in the correct quadrant. This point -724 is in this quadrant. an angle of negative 73.7 degrees is in this quadrant. So we're going to add 180 degrees. It not only gives us a positive angle, but it makes sure that we get in the correct quadrant. So adding 180 degrees to this, we get about 106.3 degrees. On this next one, if we want to name this vector u, then we have 8 square roots of 2 and comma negative 8 square roots of 2 is our endpoint of the vector. So the magnitude of u is going to be the square root of, if we square this, we get 64 times 2, which was 128, and same here, 128. So this is the square root of 256, which is 16. So our magnitude is 16 there. And the tangent of theta is the vertical component divided by the horizontal component. And this is going to be negative 1. So the tangent of theta is going to be negative 1. And if we put that into our calculator, your calculator is going to spit out a negative 45 degrees. And we don't want a negative angle. We want to get a positive coterminal angle because here we're at a positive 8 square root of 2 and negative 8 square root of 2. We're down here. So to get a positive coterminal, we're going to add 180. So theta is actually 315 degrees. Now, if you don't use your calculator, you can just go straight from here to here using your unit circle facts. Horizontal and vertical components of a vector u having magnitude of magnitude u and direction angle theta, this is true. We have A is going to be the magnitude of u times the cosine of theta. And B is going to be the magnitude of u times the sine of theta. If you want to picture this here, we can do a quick angle vector there. And we have theta here. Now the cosine of theta is going to be this adjacent right here over the hypotenuse. And that is our magnitude of vector u. So it makes sense that A, if the cosine of theta is equal to A over the magnitude of vector u, it makes sense that A is equal to the magnitude of u times the cosine of theta. And by the same reasoning, we can do the B is the magnitude of u times the sine of theta. Therefore, our vector u is the angle bracket AB. Also be found by taking the magnitude of u times the cosine of theta and the magnitude of u times the sine of theta. Here, vector v has a given direction and magnitude. We want to find the horizontal and vertical components of v. If theta is the direction angle of v from the horizontal, write the vector in the form of angle bracket AB and round to 4 decimal places when applicable. So let's try this first example. There's no picture to it, but we know that our work goes this way, that our horizontal component is the magnitude of the vector times the cosine of the angle, and the vertical component is going to be the magnitude of the vector times the sine of the vector. Okay, so we just put those into our calculator. Those are not special angles, so we're going to utilize the calculator, I get a 16.7125 for my horizontal component and a 19.9172 for my vertical component. So that's my vector written in the form of angle bracket AB. Okay, and we have this drawing here. We have a negative angle. It doesn't matter if you put in the negative angle or the positive coterminal angle, so don't let that bother you. The magnitude is U, so we're going to have 2 times the cosine of negative 140 degrees and 2 times the sine of negative 140 degrees in those angle brackets. And putting that into the calculator, I get a negative 1.5321 comma negative 1.2856. Vector operations, it's very simplified when we're talking algebraic form. If we let A, B, C, D, and K represent real numbers, we have angle brackets AB plus CD equals, we're just adding the horizontal components, adding the vertical components, that's your new vector. K times AB, so A and B both get multiplied by that K, constant of K. If our angle bracket U is A1, A2, then the opposite of U is just taking the opposite of each of the horizontal and vertical components. I can subtract angles, so we can represent that as AB plus the opposite of CD, which ends up as A minus C and B minus D. All right, given that our vector U is negative 2.5 and vector V is 4.3, we want to find the following. First, V minus U. So we get an angle bracket here of 4 minus negative 2, and our 3 minus 5. And simplifying that, I get 6 comma negative 2 in my angle bracket. And here we have some multiplication and addition going on, so it takes a little bit more work, but this is going to be a 4 negative 10 for my negative 2u, and I'm adding on to that 5 times the v vector, so that is 20, 15, and add those together, I get a 24, 5 in angle brackets as my resultant vector. Another form for vectors is IJ form. So if you have V is the angle bracket AB, then V can be represented as AI plus BJ. So the I and J vectors are unit vectors. I is the unit vector 1, 0, and J is the unit vector 0, 1. So when you're using IJ form, you're really just adding or subtracting multiples of the I and J vectors. So let's try it out in this form. If I have vectors U and V, we want to find 2U, 2U plus 3V, and V minus 3U. So first off, vector U is given as negative 1 times the I vector plus 2 times the J vector, and V is given as the I vector minus the J vector. So for part A, 2u, that is going to be a negative 2I plus 4j. So just every component, I and j, is multiplied by 2. That's it. Part B, I have a 2 times the vector u plus 3 times the vector v. And so here I have 2 times the u vector. That'll be a negative 2I plus 4j. And then I'm adding 3 times the v vector. So I'm adding 3I minus 3j. And putting those together, I get a 1I and 1j. So we have the I plus j vectors as our resultant. For part C, v minus 3u vectors. Okay. We have the I minus j vector, and then we're subtracting 3 times the u vector, so that'll be a negative 3 times negative I is a positive 3I vector, and a negative 3 times the 2j vector is going to be a negative 6j vector. And putting those together, I get 4I, 4 times the I vector, minus 7 times the j vector. And that does that. The dot product is used for other formulas. It's used for physics problems. We're just going to learn how to take the dot product. The dot product of two vectors is denoted by u dot v. That's how you read it. And it's given by the following. U dot v is simply multiplying the horizontal components together, multiplying the vertical components together, and then adding those. So you end up with just a number. There's nothing else to this. So let's try it with these problems here. If I have a negative 3, 8 vector and vector 7, negative 5, then finding the dot product is quite easy. We multiply the horizontal components together. So we have a negative 3 times 7, and we add the product of the vertical components. So you get negative 21 minus 40, so a negative 61. You just end up with a scalar at the end. Here I have vectors 2i plus 4j and negative j, and I need to find the dot product. So first let's change those to an angle bracket vector form. So this will be a 2, 4, and this will be a 0, negative 1. And when I multiply those together with the dot product, let's just change that here to a dot product right away, then it's going to be 2 times 0, which is just 0, and 4 times negative 1. So I'm adding a negative 4, and I end up with the scalar of negative 4 as my dot product. Properties of the dot product are listed here. The first product shows that the dot product is commutative. You can move those things around and it doesn't change what the dot product is. The next property says that the dot product is going to be distributive. The next one shows that the dot product is also distributive from the right. Part D of this list of properties shows that if you have k, which is a constant, times the u vector times the v vector, you can pull the constant out front and then multiply the u times the v. And then it's also the same as if you would multiply u times the constant times the v. So an associative and commutative combination of properties there. Part E shows that the 0 vector times u is going to be 0. And part F shows that u dot u is the magnitude of u squared. And now geometric interpretation of the dot product says that if angle theta is the angle between the two non-zero vectors u and v, where the angle is between 0 and 180, then the following holds. Cosine of theta is equal to the dot product of u and v divided by the product of the magnitudes of u and v. So we can find the angle between pairs of vectors very easily with this rule. So we have here u dot v. If my u is my 1, 7 and my v is my 1, 1, then I'm going to get a 1 times 1 plus a 7 times 1, which is going to be 1 plus 7, giving us 8. So the cosine of theta is going to be the dot product that we just found divided by the magnitude of u times the magnitude of v. So the magnitude of u, this is going to be 1 and 49. That's 50. The square root of that is the square root of 50. And the magnitude of v is 1 squared plus 1 squared is square root of 2. And so then I have the cosine of theta is equal to 8/10 or 4/5. And when you use your inverse cosine, we end up with a theta of about 36.9 degrees. That's the angle between those two vectors. Again, we're going to find the angle between the pair of vectors by finding the dot product. So I have a negative 15 and a positive 24, and adding those I get a dot product of 9. So my cosine of theta is the dot product of the u and v vectors divided by their magnitudes. Now the magnitudes, we'll do this, is 25 plus 144. That's going to be the square root of 169. And 9 and 4 is 13, so square root of 13 is there. And you could just put this into your calculator with the inverse cosine, and your theta is about 78.9 degrees. The dot product can tell you something about the angles. It can tell you if your dot product is positive, then you have an acute angle. If the dot product is 0, then the angle is a right angle. And if the dot product is negative, then you have an obtuse angle. So we want to determine whether each pair of vectors here is orthogonal. That's a three-dimensional word for perpendicular. So we have 1, 1 and 1, -1 as our angle vectors. And I am going to go ahead and find the dot product. 1 times 1 is 1, and 1 times -1 is -1. So when I add those, I get 0, and that shows us that these are right, or they are perpendicular, or orthogonal. And then we have these vectors 3, 4, and 6, 8. Again, find the dot product. I have 18 plus 32, and that makes 50, and it's not orthogonal. But you do know that it's a positive dot product, so it must be an acute angle. And that's it for this lesson. Go ahead and try your homework. Let me know if you have questions.